Picture a fighter jet flying through a war zone where every single GPS signal has been jammed into useless static. Picture a submarine sliding silently beneath the Arctic ice, completely cut off from satellites, hundreds of feet below where no signal is ever reached. Now picture both of those vehicles still knowing exactly where they are, down to the meter, without a single satellite involved. That's not science fiction. That's a real technology the US military has been quietly testing in 2026, and it could change the entire future of how humans, machines, and weapons find their way around planet Earth. For nearly 50 years, the entire world has run on an invisible system most people never think twice about. GPS, Global Positioning System. It sits quietly in the background of your phone, your car, your flights, your deliveries, your bank transactions, and virtually every branch of the modern military. It was born out of Cold War tension, developed by the Pentagon specifically to give American forces an unfailing sense of location anywhere on the planet. After Soviet forces shot down a civilian airliner that accidentally strayed into restricted airspace back in 1983, President Reagan announced GPS would eventually be opened up for civilian use too. By the time of the Gulf War in 1991, it was already guiding tanks across open desert and steering precision missiles onto their targets. Here's the problem nobody likes to talk about. GPS is incredibly fragile. The signals beaming down from satellites orbiting 12,500 miles above Earth are almost unbelievably faint by the time they reach your device. That faintness is exactly what makes GPS so easy to disrupt. A cheap jammer, sometimes costing less than a night out for dinner, can drown out a real GPS signal entirely. An even sneakier device can spoof it, tricking a receiver into believing it's somewhere it absolutely isn't, sending ships, planes, and soldiers confidently marching toward the wrong coordinates without any obvious warning that something has gone wrong. To really understand why this weakness matters so much, it helps to picture how GPS actually works under the hood. Each satellite constantly broadcasts a time-stamped signal, essentially a tiny whisper announcing exactly when it was sent and from exactly where. Your phone or your fighter jet's receiver listens for signals from at least 4 different satellites simultaneously, then compares the tiny differences in arrival time to mathematically triangulate your precise position on Earth. It's an extraordinary feat of engineering and orbital mechanics, quietly running in the background of billions of devices every single second of every single day. But that same elegant design is also its greatest weakness, because those signals travel over 12,000 miles before reaching you. By the time they arrive, they're barely stronger than background radio noise, roughly comparable in strength to a candle flame being viewed from thousands of miles away. Overpowering something that faint doesn't require sophisticated military-grade equipment. It can be done with commercially available hardware, originally designed for completely different purposes, repurposed by anyone with basic technical knowledge and a motive to disrupt navigation in a specific area. This isn't some hypothetical worst-case scenario anymore. It's happening constantly, right now, in multiple regions across the globe. In Ukraine, Russian forces have routinely jammed GPS signals specifically to disorient drones and confuse incoming artillery, forcing once reliable American-made precision weapons like Excalibur artillery shells and JDAM ER guided bombs to become partially or completely ineffective on the battlefield. In March of 2026, GPS jamming and spoofing disrupted the navigation systems of more than 1,100 commercial ships in a single day across the Strait of Hormuz, one of the most critical shipping corridors on Earth, responsible for roughly 20% of the entire world's oil and gas exports. The port of Doha was even temporarily forced to shut down because of the interference. Commercial pilots have reported their own terrifying encounters, watching their navigation displays confidently show a false position while flying through contested airspace over the Middle East, the Baltic Sea, and the Arctic. At least one aircraft nearly crossed into hostile territory before the crew realized their GPS had been silently spoofed the entire time. Israel eventually issued a formal warning to pilots that GPS in the region could no longer be trusted, urging crews to rely on backup navigation methods. Instead, this is not some distant future threat we need to prepare for. This is happening today, actively disrupting military operations, commercial shipping, and civilian aviation simultaneously across multiple corners of the globe. The growing crisis is exactly why the Pentagon has been racing to build something that doesn't rely on satellites at all. And the leading candidate isn't a stronger radio signal or a more heavily encrypted transmission. It's something far stranger: quantum physics. Specifically, a category of technology called quantum sensing, which measures fundamental forces of nature itself, gravity, magnetic fields, and inertial motion, rather than receiving any kind of external radio transmission that could ever be jammed or faked in the first place. The clearest, most dramatic example of this shift happened aboard one of the most secretive vehicles in the entire American military arsenal, the X-37B orbital test vehicle. This uncrewed spaceplane, often described as a miniature robotic space shuttle, launched on its 8th mission and quietly carried an experimental piece of hardware called a quantum inertial sensor into orbit. Much of what the X-37B actually does up there remains classified, but this particular experiment represents the first time this level of quantum inertial navigation has ever been tested directly in space. So how does a quantum inertial sensor actually work? It relies on a genuinely bizarre technique called atom interferometry. Scientists take a small cloud of atoms and cool them down to temperatures approaching absolute zero, the coldest theoretical temperature that can exist anywhere in the universe. At that extreme cold, atoms stop behaving like tiny, solid particles bouncing around randomly. Instead, they start behaving like waves, and they can exist in more than one state simultaneously, a genuinely strange quantum property that would sound impossible in everyday life. Using carefully tuned lasers, scientists then split each individual atom into what's called a superposition state, similar in spirit to the famous thought experiment of Schrödinger's cat, existing in two different conditions and along two separate paths simultaneously, before eventually being recombined back into a single state. Because the atom is behaving like a wave throughout this process, those two separate paths interfere with each other, creating a distinct measurable pattern. That interference pattern is incredibly, exquisitely sensitive to the tiniest possible changes in motion, acceleration, and rotation, far more sensitive than any conventional mechanical sensor could ever achieve. By continuously measuring how that interference pattern shifts over time, the system can calculate exactly how far, how fast, and in what direction a vehicle has moved, all without ever needing to look outside for a satellite signal, a landmark, or any external reference point whatsoever. It's essentially a hyper-advanced version of an ancient navigation technique called inertial navigation, where you track your position purely by continuously recording your speed, direction, and duration of travel from a known starting point. Sailors and submarine crews have used simplified mechanical versions of this idea for decades. The problem has always been that tiny errors compound over time, and a small mistake early in the journey turns into a massive positioning error hundreds of miles later. To put that compounding error problem in perspective, imagine trying to walk blindfolded across a football field, using nothing but your memory of how many steps you took and which direction you were facing. Even if you're off by just a tiny fraction of a degree at the start, by the time you reach the far end of the field, you could be standing several yards away from where you actually intended to be. Now imagine that same blindfolded walk stretching across hundreds or thousands of miles, over hours or days of continuous travel, and you start to understand why traditional inertial navigation systems have always needed periodic corrections from GPS or other external references just to stay usable over any meaningful distance. Quantum sensors solve that compounding error problem in a way traditional mechanical sensors never could, because they're measuring fundamental physical properties at the quantum level rather than relying on spinning gyroscopes or mechanical accelerometers that gradually drift out of calibration. Quantum inertial sensors can maintain extraordinary long-term accuracy over extended periods, potentially for days or weeks, without needing any outside correction at all. That's precisely why the X-37B mission matters so much. If a quantum inertial sensor can maintain long-duration, high-accuracy navigation while orbiting Earth, completely cut off from any GPS reference, it proves this technology could eventually guide vehicles reliably through deep space, well beyond Earth's orbit, where GPS signals become unreliable, or simply vanish entirely. The same underlying physics is exactly what makes quantum navigation so valuable underwater too, an environment where GPS has never worked at all under any circumstances. Submarines have always had to navigate blind once they dive beneath the surface, relying on a combination of dead reckoning, sonar, and periodically surfacing out just long enough to grab a brief satellite fix, a risky maneuver that can expose a submarine's position to any enemy watching nearby waters. If quantum inertial sensors can maintain pinpoint accuracy for extended stretches without ever needing to surface, it would represent a genuinely massive shift in how submarines operate, allowing them to stay submerged, hidden, and precisely on course for dramatically longer periods than ever before. This exact scenario has already moved beyond pure theory. The Royal Navy recently partnered with a quantum technology company called Inflection to test an ultra-precise quantum clock aboard an uncrewed submarine named Isofsnev Excalibur, operating in the notoriously GPS-denied waters of the Arctic. Around the same time, Inflection teamed up with the defense contractors Safran Electronics and Defense to launch an integrated quantum timing system capable of picosecond-level accuracy, representing roughly 1,000-fold improvement in precision compared to standard GPS timing, specifically designed for defense applications and critical infrastructure networks that absolutely cannot afford to lose synchronization. The Arctic setting for that Royal Navy test wasn't chosen by accident either. Polar regions represent one of the most punishing possible environments for any navigation system. satellite or otherwise. GPS coverage becomes noticeably weaker at extreme latitudes because of the geometry involved in how satellites orbit the planet, and the brutal cold, ice, and near constant darkness during winter months make traditional backup navigation methods, like visually spotting landmarks, essentially impossible for much of the year. If a quantum navigation system can prove itself reliable in conditions that harsh, it becomes a much stronger candidate for successful deployment nearly everywhere else on the planet, from tropical oceans to desert battlefields to the vacuum of space itself. Timing, by the way, might sound like a minor technical detail, but it's actually one of the most critical hidden functions GPS provides. Beyond simply telling you where you are, GPS satellites broadcast incredibly precise timing signals generated by atomic clocks in orbit. Signals that power stock market transactions, synchronize cellular phone networks, and coordinate power grids across entire countries. If an adversary manages to disrupt that timing signal during a conflict, the damage extends far beyond confused navigation. Entire communication networks and critical infrastructure systems can fall out of sync, causing cascading failures nobody would immediately trace back to a GPS attack. That's exactly why DARPA, the Defense Advanced Research Projects Agency, has been pushing hard on a parallel technology called optical atomic clocks, an ultra-precise quantum-based timing system specifically designed to keep functioning reliably even when GPS signals are jammed, spoofed, or completely knocked out. DARPA has been blunt about the underlying risk here, stating plainly that despite years of attempted improvements, the existing GPS timing system still carries well-documented vulnerabilities to jamming, spoofing, and other forms of interference, vulnerabilities that routinely leave warfighters without the critical timing capabilities their missions depend on. If this kind of behind-the-scenes military technology story fascinates you, this is exactly the kind of deep dive this channel specializes in, so go ahead and hit that subscribe button before we keep going, because there's a lot more to unpack here. Back on the ground and in the air, the most aggressive push toward practical quantum navigation is coming from a company called Q-Caterol, based out of Sydney, Australia. In August of 2025, DARPA awarded Q-Caterol contracts worth roughly $24.4 million under a program called Robust Quantum Sensors, or ROQS for short. The explicit goal of that program is building quantum navigation systems specifically engineered to withstand the brutal noise, vibration, and turbulence of real combat environments, not just the controlled, isolated conditions of a laboratory. That distinction matters enormously, because quantum sensing technology has traditionally required extremely delicate, carefully isolated conditions to function properly. The exact opposite environment you'd find inside a fighter jet cockpit, a moving tank, or a helicopter shaking violently during flight. Q-Caterol's product, named Ironstone Opal, uses a technique called magnetic navigation, essentially reading tiny, unique variations in Earth's magnetic field the same way a fingerprint uniquely identifies a person, combined with proprietary AI-powered software specifically designed to filter out real-world noise and interference, allowing the sensor to remain accurate even while physically bouncing around on a moving military vehicle. Q-Caterol hasn't been working in isolation either. The company has partnered directly with major American and European defense contractors, including Northrop Grumman, Lockheed Martin, and the aerospace manufacturer Airbus, running field trials of their quantum navigation technology across airborne, maritime, and ground-based platforms. A quantum systems architect at Northrop Grumman specifically described the collaboration as building a magnetic navigation system tough enough to withstand the genuine physical demands of the real world, not just survive under pristine laboratory conditions. Meanwhile, a separate but closely related effort has been unfolding above our heads. A Canadian company called SB Quantum launched a quantum diamond magnetometer into space in March of 2026, riding aboard a SpaceX rideshare mission, specifically to test how well quantum sensors can measure Earth's constantly shifting magnetic field from orbit. This experiment is directly tied to something called the World Magnetic Model, a massive, continuously updated map of Earth's magnetic field maintained jointly by American and British government scientists, a model actively used by the US Department of Defense, the UK's Ministry of Defense, and even the Federal Aviation Administration for routing commercial flights safely around the globe. That launch was actually the culmination of a much longer competition called the MagQuest Challenge, an open innovation contest, launched back in 2019 with a prize pool worth roughly $2.1 million, specifically designed to accelerate new technologies capable of measuring Earth's magnetic field more accurately than ever before. After 7 years of steady progress across 4 separate competition phases, only 3 teams remained standing by the time the final phase arrived, with SB Quantum emerging as one of the clear frontrunners heading into 2026. The company's founder described reaching that final phase as the single most significant technical milestone in the company's entire history. SB Quantum's founder described this milestone as validating their technology under some of the most demanding conditions imaginable, adding that their device could soon play a genuinely central role in how the entire world navigates across land, air, and sea. He also pointed out that the applications extend well beyond simply updating a magnetic map, touching everything from defense and civilian navigation to resource exploration and public safety operations. Essentially, any scenario where knowing your precise location matters, and satellites simply can't be trusted to provide it. This magnetic approach to navigation deserves a closer look because it works on a genuinely elegant principle. Earth's magnetic field isn't perfectly smooth or uniform. It contains countless tiny local variations caused by everything from underground mineral deposits to the shape of the ocean floor, creating a kind of invisible magnetic terrain map covering the entire surface of the planet. A sufficiently sensitive magnetometer can detect these subtle variations and effectively read them like a fingerprint, comparing what it measures in real time against a preloaded map of Earth's magnetic field to pinpoint exact location, all without ever needing to transmit or receive a single external signal. Fighter pilots have actually experimented with a simplified version of this concept for years, using magnetic anomaly detection originally designed for locating submarines as a rough backup navigation tool when GPS becomes unavailable. What quantum magnetometers offer is a massive leap in sensitivity and precision over those earlier systems, capable of detecting magnetic variations so subtle that older technology couldn't reliably distinguish them from background noise at all. What makes all of this genuinely different from previous navigation backup systems is the fundamental physics involved. Traditional backup navigation methods, like inertial measurement units built from spinning mechanical gyroscopes, have always suffered from gradual drift, small errors that quietly accumulate minute after minute until the system's reported position becomes seriously, sometimes dangerously inaccurate. Quantum sensors largely sidestep that problem because they're not relying on delicate spinning mechanical parts that wear down or lose calibration. They're directly measuring fundamental physical properties of the universe itself, properties that simply don't drift, jam, or lie the way a radio signal easily can. That single distinction is exactly why defense officials increasingly describe quantum navigation as potentially the most important breakthrough in military positioning since GPS itself was first invented. It's not just a slightly better version of an existing backup system. It represents an entirely different category of navigation, one built on principles that are, by their very physical nature, extraordinarily difficult for any adversary to detect, block, or deceive, regardless of how sophisticated their electronic warfare capabilities eventually become. Of course, none of this comes without serious engineering challenges still standing in the way. The core science behind quantum sensing has actually been well understood for years, sometimes even decades. The real difficulty has never been proving quantum sensors can work. It's been shrinking them down small enough and toughening them up rugged enough to actually survive real-world deployment on a moving submarine, inside a vibrating aircraft cockpit, or strapped to a soldier's back during an active mission, rather than sitting safely isolated on a laboratory bench surrounded by careful, controlled conditions. Cooling atoms down to near absolute zero, generating precisely tuned laser pulses, and maintaining an ultra-stable vacuum chamber. All typically requires large, delicate, power-hungry equipment, exactly the opposite of what you'd want, strapped onto a fighter jet or handheld device carried by an individual soldier. Shrinking that entire apparatus down into something compact, power-efficient, and durable enough for actual combat conditions has been, and continues to be, one of the single hardest engineering hurdles standing between quantum sensing as an impressive laboratory demonstration and quantum sensing as genuine deployable military hardware. Cost is another factor that can't be ignored here. Early quantum sensing prototypes have historically carried price tags far higher than the conventional inertial navigation units they're designed to eventually replace, meaning widespread military adoption, let alone civilian adoption, will likely depend heavily on manufacturing costs coming down substantially as the underlying technology matures and production scales up across multiple competing companies. That's precisely why programs like DARPA's Robust Quantum Sensors initiative exist in the first place. The core physics has already been proven repeatedly in controlled laboratory settings. What's genuinely new and genuinely difficult is the ruggedization process, taking technology that once required an isolated, climate-controlled lab environment and successfully adapting it to survive the extreme heat, cold, vibration, and physical shock of actual battlefield deployment without losing the extraordinary precision that makes quantum sensing valuable in the first place. There's also a broader strategic dimension worth understanding here, because this technology race extends well beyond simple battlefield convenience. Whichever military establishes reliable, field-ready quantum navigation first gains an enormous, potentially decisive tactical advantage over adversaries who remain fully dependent on GPS. Imagine a scenario where one side's drones, missiles, ships, and aircraft continue operating with pinpoint accuracy throughout a GPS-jammed conflict zone, while the opposing side's forces become confused, disoriented, and significantly less effective the moment their satellite signals get disrupted. That kind of asymmetric advantage could meaningfully shift the outcome of future conflicts, in ways not fully determined by traditional measures like sheer troop numbers or weapons firepower alone. This overwhelming strategic incentive helps explain why the American approach isn't relying on a single company or a single research lab. It's a genuinely broad, distributed effort, spanning DARPA, the Naval Research Laboratory, private companies like Q-Ketrel, Inflection, and SB Quantum, alongside major defense contractors including Lockheed Martin, Northrop Grumman, and Airbus, all simultaneously racing toward variations of the exact same fundamental goal. Multiple different quantum sensor types, magnetometers, gravity sensors, inertial sensors, and atomic clocks are all being developed and tested in parallel because different vehicles and different mission profiles ultimately require slightly different technical approaches to achieve reliable, GPS-free navigation. It's worth noting that the Naval Research Laboratory has actually been working on this problem for far longer than most people realize. Decades before quantum sensing became a buzzword, NRL physicist Roger Easton was doing foundational work that eventually led to the very first satellite ever to transmit a GPS signal back in 1977. There's a genuinely fascinating symmetry in the fact that the same research institution responsible for helping create GPS in the first place is now among those leading the charge to build its eventual quantum-based replacement, adapting an older navigation technique called inertial navigation, one that actually predates GPS by decades. Using modern quantum tools nobody could have imagined back when the original system was first designed. Gravity sensing represents yet another branch of this same broader quantum sensing family, and it deserves its own mention here because it works on a completely different principle than either magnetic or inertial navigation. Just like Earth's magnetic field, our planet's gravitational pull isn't perfectly uniform either. Dense underground rock formations, deep ocean trenches, and mountain ranges all create tiny, measurable variations in local gravitational strength. A sufficiently sensitive quantum gravity sensor, sometimes called a gravimeter, can detect these subtle variations and use them the same way a magnetometer uses magnetic variations, as a kind of natural terrain fingerprint for pinpointing exact location without any external signal required at all. It's also worth remembering that quantum navigation isn't intended to completely replace GPS overnight, at least not in the near term. Most experts describe it instead as a complementary, resilient backup layer, something that seamlessly kicks in the moment GPS signals become unavailable, jammed, or intentionally spoofed by an adversary. The US military is simultaneously working to strengthen GPS itself, rolling out a hardened new signal type called M-code specifically designed for military users, along with a more tightly focused transmission called regional military protection, expected to become available once the next generation of GPS satellites begins launching in 2027. Quantum sensing represents the backup plan for when even those improved defenses eventually get overcome. Beyond the purely military applications, it's worth stepping back and considering just how much of ordinary civilian life quietly depends on the exact same vulnerable satellite infrastructure. Commercial airlines rely on GPS for safe, efficient routing across crowded global airspace. Cargo ships depend on it to navigate crucial shipping lanes like the Strait of Hormuz without running aground or drifting into contested waters. Emergency responders use it to locate people in crisis. Financial markets depend on GPS timing. Signals to synchronize transactions occurring in fractions of a second across different continents. If quantum navigation eventually matures into affordable, widely deployable civilian technology, the ripple effects could extend far beyond any battlefield, quietly reinforcing the invisible infrastructure that keeps the entire modern world running smoothly, even when satellites fail. It's also worth acknowledging the price tag attached to all of this progress, because building the future rarely comes cheap. Between DARPA's tens of millions of dollars in direct contracts, the Royal Navy's submarine trials, SP Quantum's dedicated space launch, and the ongoing collaborations between quantum startups and massive defense contractors like Lockheed Martin and Northrop Grumman, the total investment flowing into this single corner of physics has quietly grown into a substantial line item within broader national defense budgets. Governments rarely commit this level of sustained funding toward a technology unless the underlying threat assessment genuinely justifies the expense and the sheer breadth of programs launched across 2025 and 2026. Alone suggests defense planners view GPS vulnerability as a problem demanding serious, well-funded long-term solutions rather than a minor technical inconvenience. There's a genuine irony sitting at the center of this entire story, one worth pausing on before we wrap up. GPS itself was originally born. from quantum physics, relying on the incredibly precise atomic clocks that make satellite-based positioning possible at all. Now, roughly 50 years later, an entirely new generation of quantum technology is being developed specifically to protect against, and eventually replace, the very system that quantum physics helped create in the first place. Science has a funny habit of eventually turning right back around and challenging its own earlier breakthroughs, refining and reinventing them for an entirely new era of threats nobody could have fully anticipated decades ago. It's also worth considering how differently this technology could reshape everyday civilian life, well beyond the battlefield applications that have understandably dominated the headlines so far. Self-driving cars, for instance, currently depend heavily on GPS to establish their baseline position before layering on cameras, radar, and other sensors to fine-tune their understanding of the surrounding environment. In dense cities, tall buildings routinely block or bounce GPS signals, creating exactly the kind of unreliable positioning data that autonomous vehicle companies have struggled with for years. A compact, affordable quantum inertial sensor could theoretically give self-driving systems a rock-solid backup layer of positioning data, immune to the urban canyon effect that currently causes so many headaches for autonomous navigation engineers. Search and rescue operations represent another compelling civilian application worth considering. When natural disasters strike, cell towers and GPS infrastructure are often among the very first systems knocked offline, leaving rescue teams struggling to coordinate their exact positions across chaotic, rapidly changing terrain. A rugged, portable quantum navigation device, small enough to carry in a backpack, could theoretically keep rescue teams precisely coordinated even in a disaster zone where every other digital navigation tool has completely failed, potentially saving critical time in situations where every single minute matters enormously for survivors still waiting to be found. Space exploration might ultimately turn out to be one of the biggest long-term beneficiaries of this entire technology push, even bigger than the military applications currently driving most of the funding. Spacecraft traveling beyond Earth's orbit toward the Moon, Mars, or further out into deep space cannot rely on GPS at all once they venture far enough from our planet's satellite constellation. Every deep space mission currently depends on painstaking calculations relayed from mission control back on Earth, involving significant communication delays that only grow worse the farther a spacecraft travels from home. A reliable, self-contained quantum inertial navigation system could eventually allow spacecraft to determine their own precise position and trajectory independently, without waiting on a delayed signal traveling millions of miles back and forth across the solar system, potentially becoming an absolutely essential technology for any serious future crewed mission to Mars and beyond. None of these civilian applications are fully mature yet, and it's worth being honest about that. Most of the quantum sensing breakthroughs we've covered here remain firmly rooted in defense research budgets, military contracts, and early-stage field trials rather than finished, market-ready consumer products. But that's exactly how most transformative technologies begin their journey. GPS itself started out as an exclusively military tool throughout the 1970s and 1980s, before eventually becoming available to ordinary civilians. And today, it's almost impossible to imagine modern life functioning without it. Quantum navigation appears to be tracing a remarkably similar path, moving steadily from classified defense research toward broader real-world deployment, one successful field test at a time. So where does this leave us looking ahead? The core science behind quantum navigation is no longer seriously in question. It's already been demonstrated successfully, repeatedly, across laboratories, orbiting spacecraft, submarines, and increasingly real-world field trials aboard actual military vehicles. What remains is the harder, less glamorous engineering work, shrinking the hardware down, toughening it up, driving the cost down, and scaling reliable production up to the point where quantum sensors become a standard, dependable piece of equipment rather than a delicate experimental prototype. Based on the sheer pace of contracts, funding, and successful field tests happening throughout 2025 and 2026 alone, that transition appears to be arriving considerably faster than most people outside the defense and physics communities currently realize. The next time you glance down at a blue dot, confidently telling you exactly where you are on a map, it's worth remembering just how fragile that seemingly simple convenience actually is, and how an entirely different branch of physics, one built on cooled atoms, laser pulses, and the strange, ghostly rules of quantum mechanics, is quietly being engineered to make sure that blue dot never disappears completely, even in a world where satellites can no longer be fully trusted. This isn't a distant, decades-away possibility, confined to theoretical physics journals. It's happening in active field trials right now aboard spaceplanes, submarines, drones, and aircraft, funded by real government contracts and tested under real combat representative conditions across 2025 and 2026 alone. What started as a Cold War era tool for guiding tanks across the desert is now quietly being reinvented from the ground up, this time using the strangest, most counterintuitive branch of physics ever discovered. The atoms don't care whether a jammer is broadcasting nearby, the magnetic field of the Earth can't be spoofed by an adversary's radio transmitter, and gravity itself has never once lied about where you actually are. That's the quiet promise sitting underneath all of this research. A navigation system built on forces of nature that no enemy, no matter how sophisticated, can ever fully switch off. If this story opened your eyes to a piece of military technology quietly reshaping the future, go ahead and hit that like button and make sure you're subscribed, because these are exactly the kinds of breakthroughs this channel exists to uncover. And I'll see you in the next one.